Hello. So in this video, I'm going to discuss chapter 23, electrical resistance, and I'm going to introduce you Ohm's law. Electrical resistance. I'm going to start with electrical resistance. And electrical resistance depends on the two things, material and the geometrical shape of the material. Those are the two things that determines the electrical resistance. So when you have a conductive material, we say conductive material, it has free electrons. So electrons are free to move. So when you apply potential difference, the voltage difference, you're going to have a flow of electrons, which means you're going to have a current, right? But that flow depends on what material or what electrical resistance is. As you can imagine that I mentioned that current, electrical current is very similar. You can imagine like a water, like a river. But no river has zero resistance, right? Some river has some kind of they're rocks or it's just a weird shape that you don't have a water flow perfectly. You're going to have some kind of a resistance. So that rocks and all those things is similar to the electrical resistance. That depends on the material and the geometrical shape. You're going to have a different resistance. So let's go into the board again, and I can show you in there better. Okay, share the screen. Sorry, it's taking time. Should have done this earlier. Okay. Okay, so this is chapter 23, electrical resistance. Chapter 23, electrical resistance. I'm just, so again, electrical resistance depends on the two things. Resistance depends on two things. The material and its geometry. It is true. It is also depends on the temperature and all that too. But typically it depends on the material and its geometry. So again, to have a current, you have a free electron. So we typically talking about conductors, right? That you need to have a free electron. So you have to have a motion of a charge. In order to have a motion of a charge, you need to have a conductor. And there are different kind of conductors, different kinds of metals, right? So for example, when you have a copper wire compared to the steel, they're both conductors, but copper has less resistance compared to steel. And this is true for the same size. So depends on the material, you can imagine. And okay, so let's imagine this is like a river, right? You have if you have a height difference, you have a water flows. Water flows from the height difference. So like a river that has like a height difference, right? Like this. The coming down, then the water flows. If it's completely flat, you need to have inertia. That's it. But to maintain the flow of the water, you have to have a height difference. And these rocks, there's these rocks in the river. There are these rocks in the river. They're like their impedance. That gives resistance, right? It's make it harder for the water to flow. So you can imagine that current too, electric current too, that if you have a lot of like lattice or all those things, that makes it harder for electrons to flow, charges to flow. So that is depends on the material. You have a different kind of impedance, and it just happens that copper has a lot less resistance than the steel. And if you can, so like you, most of the wire you see is a copper wire, right? One, it has less resistance, but also it's cheaper material. You could have a very, very good conductor that has a lot less resistance, but if it's very expensive, it's not so practical. So that kind of a thing. Now, so you see that it depends on the material. You have a different impedance, resistance. How about for the same material? For the same material, let's see. Imagine if you have a longer wire. So imagine that you have to go through this, this river has to go through the rocks and in a longer distance compared to if you had to go 1 meter versus 2 meter. What do you think? Is it harder or easier for the water to flow? You have to go longer distance. So like a longer wire, you're gonna have you gotta go through another distance, right? More distance. So you can see, I hope you can see that longer the wire, it means higher the resistance. And also wider. How about when you have it wider? When you have it wider, that means that you have more options to pass through. So the density of a rocks, like the impedance is about the same, but you have more options. There are more options to go. So wider the wire, it's going to be lower the resistance. And that's like you're at Target and there's a bunch of cashiers available versus you only have a few, two registers compared to if you have it more available. Maybe they're all the similar business, but if you have more options, you're gonna go with the one with um, mm, more options. So wider the wire, you're gonna have a lower resistance. So I mentioned that the resistance depends on the material and its geometry. Here, just in case, also also depends on the temperature. As you can imagine, what do you think? Increase in the temperature? What do you think? If you have a higher temperature, what happens to the resistance? What do you think? Imagine that these rocks are there, right? But then in a river, and then but if you have a higher temperature, what does it mean? Is that these rocks also have some kinetic energy, and higher the temperature, you have more kinetic energy. So even though the size of the rock is this much, but if it moves more, it's gonna cause harder for the current to flow. So increasing temperature is increase in resistance. Um, lastly, um, lastly, electrical resistance, electrical resistance. I'm going to use the alphabet. Typically, it's use the alphabet uppercase letter R, and unit to describe, it's also a scalar. Unit to describe is ohm. This is the Greek letter omega, uppercase omega, or the Greek letter, and that's what we use. So you might hear like a example is like 10 ohm, 15 ohm, that kind of a thing that you might see. Let me see. Sorry. Compound. If I can just take this out. Let me see. I can show you. Or how can I show you this? We'll see. Share another screen. I wonder if I can just show this. Hold on. Try again. So here, I wish I could just show you this here. No, this is the one. So this is in a circuit board. You put this kind of items as a resistors, and these there's a color coded. These are all color coded. Means that sometimes this brown over here means K, or you know 10K, 20K, like that kind of a thing. And like orange means 1 or 2 or 3, and then this means 0 or 7. So if you memorize it, the color coding, you can just look at this device and says that, okay, this is 275 ohm or 275 kilo ohm, that kind of a thing. If I can show you this, resistance circuit. Image. Yeah, so it looks something like this in a circuit board. Come on. Yeah, so like this thing here, that there's a circuit board and you have these items, and this is the resistors in the circuit board. And then you have these are made of metal so that the current can flow and then pass through this, so you can have certain kinds of electrical resistance. And these resistors how do you control the amount of resistance? Typically, they put the carbon powder, and you control how much carbon powder, and you might put some metals in it to control the amount of resistance. That's how they make this resistors. All right. And let me see. Lastly, so then, yeah, depends on the case. You use this kind of a thing to have a certain flow of a current, and because we're designing certain electronic device. How do we do that? And so here is the Ohm's law. Ohm's law. What Ohm's law says is current equals voltage. When you say voltage here, so this means voltage drop, change in voltage, divided by the resistance. This is what the Ohm's law is. I equals V over R. I'll say change in voltage. Okay. So you can see the 1 ampere is also equals to 1 volt per ohm. Oops. Okay, my son might be waking up. Okay, I'm going to stop a little bit over here for now. I'll come back. Okay, so I'm back. Ohm's law. Ohm's law is, let me see. Ohm's law is, show you here again. This is Ohm's law, right? Current equals voltage, in this case, voltage drop, change in voltage, divided by the resistance. So then more drop, more voltage drop means more current can flow. And the bigger the resistance, you're not going to have as much current flowing. So this kind of a stuff should make sense to you. By following this Ohm's law, you can design a circuit that, okay, this for this electronic device, maybe it's a light or light bulb or whatever that that you're designing. You can control the amount of current by putting different kind of a resistance, or how you control the voltage drop on that spot. So we use this Ohm's law. One thing about Ohm's law is that though it's not a fundamental law. It's not like a Newton's first law or gravitational universal gravitational law or Coulomb's law that applies to anywhere, anytime, or everywhere. It's not like that. It's not a fundamental thing. It's actually an empirical data that only works in a certain regime, especially like in the room temperature. With most of the materials, it works, but when you talk about like in a cold temperature or like a superconducting material and all that kind of stuff, then it may not work. Okay, but this is the Ohm's law, which is the current equals potential drop divided by the resistance. And this is a very, very useful equation. All right, so this is the end of this video, and I guess I'm going to see you in a discussion.